Thank you. Thank you guys for coming again to the talk. So this will be a little bit more into the details of what is the architecture of the new logging service. So I couldn't speak about this during the keynote, so here maybe you can take away a little bit more, take home some kind of design details or choices that we've made when we designed this product. So the agenda for this is a little recap of what actually logging service is. Then I'll speak about the architecture, a little bit into the metadata service that we have and the ingestion API, and then what we do with Spark extraction API, how we amend it a little bit in order to make the extraction a little bit easier for our data scientists. So what is, again, this controls data logging? You probably remember from the keynote already, so I'll quickly go through it. So we have those devices, and we actually do kind of readings on them. So we kind of subscribe to them, and we get readings. And that readings we have to present to the operators in order to operate the machine. Or there are other various studies done on historical data. Like designing new beam types, experiments, designing new machines, and so on. So this is actually required if you want to do quality operations there to deliver the beam to experiments. So the beam has to have certain characteristics, and those readings help operators and physicists to tune it the way that are actually accepted by the experiments. So this is before we take data from experiments. This is just to emphasize it once again. So we had this old logging service, NXCALS, that again I here repeat the numbers that we have in it. So around 20,000 devices that we subscribe to. 1.5 million signals, 5 million extractions per day, so queries that we get from various sources. 71 billion records in average that will give us 2 terabytes and 1 petabyte of stored data long term. Okay, so why we do it again? Because we see, so why we do the new system basically? Because we have seen a dramatic increase of data loads during run 2. And we have to adapt to this situation somehow. So the issues also that we have seen are related with scalability. We try to tune the databases, the Oracle databases, but this is not easily scalable in our environment. And actually, there are also some other issues, like we see more and more really big payloads that we get. This is related with the number of bunches also that increase in LHC. We get bigger vectors that we have to store, and there are some kind of rigid table structure in the old system, and we have only basic types. We do not support nested types. And also integration with other tools that other people actually use for analytics is not very good. So those are the problems that we are actually confronted with. And because this is like designed from 15 years ago, that you actually had to extract this data to do the analytics. So people first read the whole data set, and then they analyzed it, somehow stored it locally, and then analyzed it. So this is not very good for big data, and this is a big limitation for us. So we wanted to remedy this, so we looked into different tools that were actually available. So this project started around 1.5, 2 years ago when we started to look into that. We didn't know anything about that domain. So we learned that all. We kind of analyzed what is available. We tried to go with some proof of concepts in order to choose what is the best for us and maybe also what is the safest, because this system will be with us for the next, I don't know, maybe again 15 years or even 30 years. So this brings us to this design that is this next logging service that is based on Kafka, Hadoop, and Spark. So again, coming a little bit back to what is this controls data in order for you to understand what is the domain and what we have to store. So the readings come from devices, but actually devices, they have properties. And a property is like a structure that has many fields inside. But basically, the values that we read, you can look at them as time series of records. So you get events from those properties that actually advance in time. So for a given device property, and you get records that have some timestamps and values inside. Okay, so different fields with different values. But this is one type of schema that you can get. But over time, that device can change, or device property can change. So the hardware gets updated, the software as well, maybe even independently, and the given property can be changed. So after some time, when you subscribe to this property, you will see a different schema, so different set of fields. And this can go on. So over time, what we have to store and actually extract later on can actually change. So we see a lot of those schema changes. So this device change over time. So this is a takeaway from this slide. So also, this is really a multi-schema domain because of other facts, because we have many devices that have, at the end, many properties. And those properties are also different. So each property will actually have a kind of schema that is related with it, so different set of fields. And this brings us to this conclusion that we have really a variety of different schemas that can change over time. So that's actually the domain, and you have to understand in order to kind of understand why we took this design. So then, why I'm speaking about this generic storage system? I mean, this was an idea that kind of struck us when we actually realized, or we knew it, that actually we're not only storing device property model, because different groups at CERN actually control their equipment also with different control system. It's not always device property model. So we said, okay, let's take a step back and maybe design something that is more generic. So let's provide some abstraction into it. So this abstraction we called entity. And what we store is just records that are related to this entity. So like an event in time that change. And at the end of the day, the record is composed of some key that is like an entity key, corresponds to an entity, and it will have some values. Of course, since this is like time series, it has to have timestamp inside. And we want to partition those records somehow smartly, so it will have some partition information as well. So this is not limited to controls nor CERN, so maybe you can recognize some of this in your domain. So there are some requirements, of course, that are really related with how we want to operate the system and how we want to make it, let's say, less complex for the users in order to send data and extract data. So first of all, you would like to discover entities from records. So if you have some ingestion API, you would like to just throw some records on it, and you don't want to register your entities in advance. So we said, okay, let's go for it. It's much easier because in the old system, we actually had to go through some registration procedure in order to register the variables or the signals that we would like to log. This is completely not good. So obviously, once you have your entities, you would like to search for them. So check what entities are registered, how they are partitioned, with what schemas they are actually saved. And then obviously, one more thing, you want to store the data for it. That's quite obvious. And then, so those are the requirements that we have that actually span the type of usage that we have in the system. So we have this online monitoring and offline access. And online monitoring is more on the side of low latency data that has to be available for extraction. So there is, let's say, a bit less analytics done there. But on the other end, you have this offline analysis where we have more complex analytics tools that are needed and maybe more visualization tools to kind of attack this problem. So that's how we went into this architecture. So we have actually some data sources that are subscribing to our devices, and we provided some Java ingestion API that is quite simple, that just accepts records, and behind the scenes, it's actually sending those records to Kafka. So they are stored in Kafka, and then we have ETL processes that send this data later on to Hadoop, to HBase and HDFS. So this is not like we send from HBase then to HDFS. So there are two ETL processes, two types of processes that are sending data to two destinations at the same time. So this is like, let's say, a Lambda architecture, if you want. So then we have Spark. So we have extended Spark data source API in order to hide those details from our clients. So the clients do not know what's the storage behind. They just want to read values, read their entities, and that's it. So we use Spark for that, and we use Jupyter. And this is all governed by this metadata service, where actually this piece of software is responsible for registering the entities from the records, and schemas, and partitions, and so on. So there are some design choices. You might ask yourself a question why we selected those tools. So why Kafka? Okay, this is widely known, but okay, maybe I'm repeating some obvious things, but we debated a little bit whether we need this component because, okay, the more components you have, the more moving pieces you have in your system, the more it is kind of exposed to different problems and errors that come with them. So there is, let's say, this data redundancy and data safety, basically, that is coming with Kafka, because if we have a problem downstream, we can still keep data in Kafka when we don't lose it. And also, there is one possibility to implement the very low latency streaming API just based on Kafka. So we have it in mind as well, because there are clients that really rely on very, very low latency. So this data can be then presented to them directly from some Kafka topic and partition. Then why HBase? Okay, this is quite fast key value store. Over our tests, I think this was one of the best tools. So we looked into Kudu as well, which was actually presented on this conference. But okay, at the time where we had to select something, it was quite limited. It was in a beta version, limited types, and maybe some other things I don't actually remember right now. But okay, we went for HBase, and this HBase also buys us the time that is needed to do the duplication and compaction of what we actually store in files in HDFS. Okay. So then, at the end of the day, the data long-term is stored in Parquet files. So this is, okay, was already presented, so I don't have to repeat that. What is good from it is this predicate pushdown and column projection, which is very fast for analytics. And at the end of the day, it's quite easy to understand and an open format that if at the end of the day somebody cannot use Spark, or Spark is not the most sexiest tool right now, we can still use those files. That's at least the idea behind this. And it's, of course, easy to back up and so on. So what are the data flows? So okay, this is quite easy. We have an ingestion API. We send it to Kafka. Then the ETL extracts towards those two destinations at the same time. Then we store it in Avro in some temporary folders. Then we deduplicate. We compact it into larger files. So of course, this is kind of trying to be Hadoop friendly there to create big files instead of many small files. And then we use extraction for data access, and then this meta service is actually kind of in place for the missing indexes as well. So it actually knows where the entities are located. So we don't scan many files for nothing, actually. So we know exactly if somebody looks for a given entity, we point it to a given file where this entity is exactly located. Okay, so one slide here on the DevOps. It's a bit out of topic, but okay, I thought this would be maybe also interesting how we do this. So it's a microservice architecture. So basically what we found out is that the monitoring is actually crucial here. There are many let's say, clustered services here, many moving parts. So you have to understand what is going on in your system. So we use this technology stack in order to do this. And then it's fully automated with Jenkins and Ansible. So if you wonder whether you can use those tools, I mean, it's working quite well. So a takeaway here is to automate as much as you can. So now going to the metadata service. So we have, just to recap, we have two kind of data, let's say data types. So we have obviously the events, the records, and that goes to Hadoop, HBase, Kafka, and so on. And we have the metadata. So this is the information about the data. And this goes to some relational database, in our case, Oracle. So just to recap on the domain again, so the system stores changes of state of some abstract entities in form of records, let's say, that are identified by entity keys and timestamp. So this is like a extended data series, so time series data. Then a record can have an arbitrary number of fields, where some fields are actually special. So you have entity keys, partition keys, and timestamp that are special. So the whole thing forms a schema, of course, and actually records are split, so partitioned on disk based on the time, the partition key, and the schema. So this is how we do this. And fields obviously can change over time, so we have to keep the history of schema changes over time as well. So what objects we have in our relational store? So we have definitely the entity, which is kind of the main object around which we store the data. This is identified by some arbitrary fields from the record. Then we have a partition. So this is, again, some field from your record by which you would like to partition your data. Then we have a schema. This is quite obvious. On top of that, we have what we call system. So system is something that actually defines what is the entity key, what is the partition key, what is the timestamp key from your record. Okay, because we can have different people using this system, sending from different controls system, or sending records of arbitrary structure, and it is up to them what it means for them to have an entity key. What is this entity key? What is the partition key? We keep, of course, the entity history, so all that schema changes and partition changes for entity over time. And we have a concept of a variable. So variable is like a pointer to an entity. And this is quite useful in our domain, and maybe you can recognize this as well, because this pointer can point to a whole record or a field in a record. And this thing can change over time. So you can have a variable history and a configuration that changes over time. So you can have some abstract variable, and you don't have to remember what was the entity behind it. So there is a Java ingestion API example here. So how it looks like, you create a publisher for a given system. So a system is something that tells you what are the entity and partition keys. So you have to, and then you create a record. So this immutable data is like a map of string object, let's say. So you, for instance, in the device property model, you say you want to store some data for a device named like that, property setting. Then a class and property form a partition key. Okay, and then you give it some timestamp. Let's say it's a record from now. Then you add some arbitrary fields, and then you just publish it. So this is also where the system discovers the entity. So inside there is some mechanism to discover if this entity that is called NXCALS monitoring dev1 is not registered, it will actually register it. And then you handle some errors. It's a completable feature, so you can handle errors there. So coming a little bit on the partitioning, you recognize some of that. We have the record that is composed of entity key, partition key, timestamp, and fields. So this information is stored actually in our Metastore, and on disk it ends up here. So we have let's say a system ID goes to some SID, then the partition key gets into some kind of a partition ID, and so on. So we have a schema, and then the time goes there into a date. So we partition actually by day, but okay, this can be changed over time. And then the data gets into the Parquet file. So basically, if you take an example from a device property model, so entity key is device property, partition key is class property. So class is like in a programming language. You can have a class, and then device instantiates this given class. Okay, so let's say the property of this system is that a given file obviously will contain records of the same schema, always. So that's by definition of this. Then this Metastore, okay, you have to, if you send many, many records, this has to be efficient. You cannot contact the database with every record. So the metadata is cached, and we call this service only on entity creation, entity change, or cache misses at the beginning when you start up your process there. You're going to have some cache misses. So actually, this service is called rarely. So that's the very important property of it. So, and then we have those features that entities are dynamically created, schemas are discovered, records can change, and schema changes are actually handled at extraction using the history of the schema changes. So now, for Spark extraction, so we have created a data source extension to Spark that was already shown, I think, during this conference. So, okay, I'm not going to read it for you, but this is how you normally instantiate it. And that hides the details of how we get the data. So I'm repeating a little bit. So we store the data in HBase. So we extract data from HBase that is not older than 36 hours. We are using also the Hortonworks connector. It works quite well for us. And then older data is actually extracted from HDFS. And in this extraction, we merge the schema using the schema history, which actually greatly simplifies data access. So just to visualize that, we have this. So okay, in 36 hours, up to now, the data is in HBase. Later data is in HDFS. And then when somebody asks for the data set that actually spans those two data stores, we underneath actually create two data sets, then we union them, and then the user actually sees just the output data set without knowing actually where this data is coming from. I give you some example. Like you've seen how to send the records, now you can see how to read them. So actually we have a builder on top of Spark, so you don't have to specify this format and so on. So you have to say which system you're trying to access. You give those entity keys. So again, it's the same entity. So you would like to search for events for this entity. So this device property in this example. Then you would like to say, okay, what is my time span, time window for which I want to get the data? And okay, here you can even filter some entities. So this is like pre-filtering. You don't fetch all the fields or the fields you're not interested in. And then you just say, okay, build data set. And from now on, you have the data set for whatever you want to do with it. So any analytics, this is based on just Spark API. Okay, so you get the data in the following format. So this, I think, simplifies a lot. Coming back to the schema merging. So this is quite important. You've seen that the schema might change over time. You might have different number of fields. And in order to merge it with Spark, might not be so easy sometimes. So it evolves, let's say. You have a record with 2 fields. Later on, you have a record with, okay, maybe a little bit changed fields. So you have a rename of field 2 to field 21. Then later on, okay, the designer of the class and device property said, okay, I'm going to change it all. I'm going to have another field, which is absolutely different from the fields that we had before. Okay, if you want to extract it, is it easy? Okay, I mean, sometimes you can end up having some exceptions. Okay, like for instance, this one that you cannot union this data because you have a different number of fields, of columns. Of course, this can be done. You can do it. You can apply some logic on the data sets and do it yourself, but it's cumbersome for the data scientist. So what we want to do is to do, let's say, basic amendments to this that we do internally in this data source API. So in this example, the first improvement can be that you actually return a data set. You don't say, you can't merge it because you have a different number of fields. So here, we try to do this by, of course, replacing the missing fields by nulls. But okay, that's quite simple, but at least it's an improvement number 1. But you can do a little bit better because, okay, you can observe here that the field 2 and field 21 this is actually a rename. So you can maybe merge those 2 columns together. And this is what we do as well. So in this example, those 2 fields are merged into what we aliased as new field. Okay, and this is where you get the happy faces from your data scientists. Huh? Okay, so going to variables. So this variable, maybe you understand what it is, but I wanted to give some example here. So again, it's a pointer to a given entity record or field in some time window. And you don't need to know the real entity, and it's quite useful for some abstractions. Okay, we have high-level managers that do not want to know what is the exact device that is responsible for this, but they want to know what was the LHC beam intensity. Okay, and this is quite easy for them to know, okay, I have this variable, I can extract it. So kind of symmetrically to the entity extraction API, we have this variable extraction API, which you can maybe guess it's quite similar. So you specify a variable key. In this example, you don't give a system because this variable can point to many entities from different systems over time. Then you specify the time and you just extract it. Okay, you build data set, of course, and you can do different operations on this data set. So the changes of the variable you can visualize like that. So you have an entity number 1 with some fields, so the variable can point to this field 1, and in some other time can point to field 2, and again to a different field over different time period. Okay, and then still you can observe the extraction that will actually give you the data set already correctly merged. Of course, you have to merge the types, but we do also our best to merge the types here. Okay? So why this simplified extraction? Okay, this is maybe a case for us, or you will recognize it as well for your domain, is that the data producers are not the same as data consumers. So the data scientists, somehow they might be detached from the guy who actually produced the data. So there is some loss of meaning what this data means and what the schema meant at the given point in time. So this happens at CERN a lot, that we have equipment groups and designers of equipment, let's say device properties that are quite low level. And they don't care, or they kind of don't, so this information is not propagated very well to the people that actually do the physics and beam-oriented analysis. Okay, and this is why it's very important to remove this complexity and to have the system unified and as simple as possible to be, let's say, to achieve the best level of usability. So I summarize here by saying that this new system is quite generic. Big data storage system hides a lot of details. You don't have to really understand what's behind the scenes. And we store this time series-like records of changing structure with arbitrary entity and partition keys. We have currently a Java ingestion API with Spark extraction API that is available for Java, Python, and Scala. Yes, okay. And if you want to take a picture. And then, okay, that's it. If you have some questions, or you can have a look at the source code. The system is still in its early beta version, but we have deployed it already for some clients, and we are trying different things here. So maybe the APIs will change a bit, but okay, who knows? We're trying to make a productional version as soon as possible. And if you're interested, just drop me an email. Or maybe we can discuss now if you have questions. Thank you.
All right, if there are any questions, there's a mic there, as well as a mic here, or you can come up here for questions.
So who keeps track of actually what field is what? Like if it is a pressure sensor or a Faraday cup or something?
Yeah, we have a database that is like controls database, which actually serves as the information source. Okay, but where you will see that, for instance, for a given property, you'll see many fields that are called current A, current B, current C, and so on. So, and then you have to talk to the designers of the class in order to understand what current it actually it means. I mean, the guy who extracts the data has to contact the guy who designs the class. There is some description, but sometimes it's not filled in or not really relevant, or maybe not explicit enough to understand, is this the field that I'm interested in? But this is a very complex problem that we are trying to solve right now by improving this controls information database, let's say.
How do you figure out the changes in the schema? You said the schema changes in the input field API. So how do you configure that and capture that?
Yeah, so we figured that out by looking at the set of fields. So basically, when you send your records, if the entity is not registered, we register it. And we know that we register it with schema A. Okay, and we keep it in cache. So this is cached on the Ingestion API. Okay, so we know that every time you send the record, we check, okay, do we know it? Yes, we know it. We have it in the cache. Do we know the schema? Yes, it's the same schema. And then if we discover that somebody sent the record for a given entity with a different schema, then we register new schema, basically.
Okay, so it's done in the Java API that you have written?
It's done in the Java API, so this is just for performance reasons, let's say.
Okay, so the API at the time of receiving it compares to all the schemas and then figure out.
Yeah, it compares the schema for the entity it knows, not all the schemas, just the schemas that it deals with.
Any more questions?
Yeah, so for the schema controls, I'm just wondering, do you have some restrictions around things like, let's say, non-null values? So like maybe fields can never be null, or if there are more semantic validations? So like, for example, if the loggers suddenly start changing the date format, or they start logging in epoch time instead of string dates, and if that is the case, how do you manage that, especially across schema evolution?
So basically, I mean, what we store is an Avro schema. So that's point number one. Secondly, we have those special fields. So if you defined your system, let's say, for an entity key, you said, okay, I'm going to use device property, and then those are strings. And then if you try to send longs for this, we will discover that, and we will tell you that that's a wrong schema, and we will reject this record, basically. So for special fields, the field types, the field names have to be present and be corresponding to your system definition. For all the other fields, we just bluntly accept it. And then you can have problems at extraction, of course, but this is another set of problems, let's say, you might have. So basically, we of course, discourage people from changing the schema in a very incompatible way. Let's say, because you might imagine you have a field that is a long, and then this field might be of a nested structured type. And we will never be able to merge this during extraction. And of course, those problems are there, but you can't fix it. I mean, this is, the system is open, it allows you to do this, and later on, it's up to you. I mean, it's like you crap in, crap out to a certain extent. Yeah.
So for some things like, let's say if somebody wants to add a new field, but they want it to be a required field, right? So like in Avro, you can say a field is null or nullable or not nullable, right?
I mean,
so can you do things like how would you then extract the old data that no longer has that field if on the query side it's expecting it's a non-nullable value?
Yeah, I have to dig into my memory now, but I think that all the fields are made nullable at the end, because I think it ends up in a Parquet format, and in Parquet I think all the fields are somehow nullable, and this is solving this problem to a certain extent. And okay, the system is, so we rely on the client to check for its data, let's say. We don't do a lot of sophisticated checking in this system, because maybe it's not the place to do it at the end. I mean, we do some checks. Like, for instance, you want to send a timestamp that is negative, and we're going to reject that, of course. And then those types that I already mentioned. But the rest is the client responsibility to do it, because we want to keep the system as simple as possible. Yeah.
So what are you using to move the data from Kafka into HBase and HDFS? Because I didn't see it on the schema. Is it the same Java API or?
No, we use LinkedIn Goblin.
Okay. That should appear on the schema.
Yeah, okay, I didn't want to say this. Is there any LinkedIn guy here? Okay, we had a bit of problems with Goblin, so we are thinking about changing it into our own implementation, let's say using, I don't know, Spring Data or Spring Kafka. This should be quite easy. But originally we taken this design choice, and that's why I don't mention it, because I don't want people stick to that.
Final question.
So you're not considering using Spark streaming for that job?
Yes, I'm here with my colleagues, so we had some discussions whether, we consider that, but okay, this still is an open question. So far we managed to maintain Goblin in a state where it does what it does and it's fine. But later on, I think there's going to be a step to choose another technology for that. And yes, Spark is an option here, I think. And we are maybe after this conference a little more into this than other solutions. But.
All right. Thank you, Jakub.
Thank you.